Welcome back. This module is one of the highest yield chapters in the entire syllabus. Let us earn it. Have you ever glanced down at a car's speedometer and wondered what that needle is actually measuring? It is not telling you your average speed. It is telling you your speed at one exact, frozen, fraction of a second. That single idea, measuring change at an instant, is the beating heart of calculus. Today, we master the derivative. Picture any curve. Y equals f of x. Forget formulas for a moment. Just look at the shape. Drop 2 points onto it. P, at x, comma, f of x, and Q, a small distance h further along, at x plus h, comma, f of x plus h. Join them, and you get a secant line. Its slope is simply rise over run. F of x plus h, minus f of x, all divided by h. That is the average rate of change. Useful, but blunt. It tells you nothing about what is happening at P itself. Now watch this. Slide Q toward P. Closer. Closer. As h shrinks to 0, that secant stops cutting the curve, and begins to touch it. The secant has become the tangent. And that is the derivative. F prime of x equals the limit, as h approaches 0, of f of x plus h, minus f of x, all over h. In one sentence, the derivative is the exact slope of the curve at a single point. One condition, and the paper setters love it. That limit must exist from the left and the right. If the two sides disagree, a sharp corner, a cusp, the derivative simply does not exist there. The derivative itself is just a tool. The marks live in what you do with it. 4 families. 1. Rates of change. A balloon inflating, a ladder slipping down a wall, a shadow lengthening at dusk. Anything that moves, changes, or grows. 2. Tangents and normals. The geometry of touch. 3. Monotonicity. Proving, with certainty, that a function is strictly increasing, or strictly decreasing, on an interval. 4. Maxima and minima. The peaks and the valleys. Today we drill families 2 and 4. The two that appear almost every single year. Let us take a classic. Read the demand before you touch your pen. They want a normal, and they have told us it is parallel to a given line. Parallel means equal slopes. That one word is the hook the entire question hangs on. Step 1. Differentiate the curve. dy by dx equals 3x squared, minus 3. That is the slope of the tangent at any point x. Step 2. The normal is perpendicular to the tangent, so its slope is the negative reciprocal. Minus 1, over, 3x squared minus 3. Step 3. Handle the given line. x plus 9y equals 15, rearranges to y equals 15 minus x, all over 9. Its slope is minus 1/9. Our normal is parallel to it, so our normal's slope is minus 1/9. Step 4. Equate them. Minus 1 over 3x squared minus 3 equals minus 1/9. Cross multiply. 3x squared minus 3 equals 9. So 3x squared equals 12. X squared equals 4. And x equals plus or minus 2. One quiet check that separates a topper from an average scorer. The normal's slope has 3x squared minus 3 in the denominator, so x cannot be plus or minus 1, or the tangent is horizontal and the normal is vertical. Our roots are plus or minus 2. We are safe. Step 5. Feed those x values back into the curve. Never into the derivative. At x equals 2, y equals 8 minus 6, which is 2. At x equals minus 2, y equals minus 8 plus 6, which is minus 2. 2 points of contact. 2, 2, and minus 2, minus 2. Step 6. Point slope form. Y minus 2 equals minus 1/9 times x minus 2. Now clear that fraction. Examiners want the standard form. That gives x plus 9y equals 20. And by symmetry, the second point gives x plus 9y equals minus 20. 2 normals. 4 marks. Secured. Second problem. Find the local maximum of this cubic. Before any algebra, look at the picture. At the very top of a hill, for one instant, the curve is flat. Flat means slope 0. Slope 0 means the derivative is 0. Step 1. Set the first derivative to 0. F prime of x equals 3x squared minus 6x minus 9. Divide through by 3. Always simplify before you factorize. X squared minus 2x minus 3 equals 0. That factorizes to x minus 3 into x plus 1. Critical points. X equals 3 and x equals minus 1. Careful here. These are only candidates. A 0 slope could be a peak, a valley, or a flat shoulder that is neither. We must test them. Step 2. The second derivative test. F double prime of x equals 6x minus 6. At x equals minus 1, minus 6 gives minus 12. Negative. Negative second derivative means the curve is concave down. It is holding water upside down. That is a peak. And at x equals 3, 12. Positive. Concave up. That one is a minimum. Step 3. The question asked for the value, not the location. So substitute minus 1 back into the original function. Minus 1, minus 3, plus 9, plus 5. The local maximum value is 10, occurring at x equals -1. Two distinctions that cost students marks every year. -1 is the point of local maximum. 10 is the value. Read which one they asked for. And second, this is a local maximum only. A cubic over all real numbers shoots off to infinity in both directions. It has no absolute maximum or minimum. Never confuse the two. 3 things to carry out of this module. 1. The derivative is the exact slope of a curve at a single point. 2. The normal's slope is the negative reciprocal of the tangents. 3. The first derivative finds your candidates. The second derivative decides their fate. Next module, we put this tool to work on rates of change. Practice these 2 problems until the method is automatic. See you there.